Thank you, Flora. And so I will start this presentation to so thank everybody for being here today with the strike. It was not so easy. Thank, of course, the people online and start by thanking also CY.
Non, ça dure 1h30.
Start CY.
Je le verrai en replay.
Claude, your microphone was on. Okay, so yeah, I will talk today about smart electroactive polymers that are doing different things, especially contract, expand, sense, and self-heal. And indeed, this is a work that is developed at the LPPI here at Cergy Paris University. So just a few words to introduce the laboratory. We're a laboratory of polymer chemistry, physical chemistry, and studying also interfaces. And the main focus of the lab is the synthesis and characterization of multi-component materials for different kind of applications. I will mention a few of them here. So for cultural heritage, for ionic conducting membranes for batteries and fuel cells, energy storage for supercapacitors, photovoltaic, organic photovoltaics to convert solar energy into electricity, and also on smart materials. And this is what I will talk about today. So I will start with a simple definition. What are smart materials? Because that can be surprising to think about materials being smart. It's just on the opposite of passive materials, like the materials we know, like wood, metals, conventional plastics, and so on. Here it's simply materials that can adapt or react to a change in their environment or to an external stimulation. And it sounds a bit new, but finally it's not that new, because if we look at these materials, some crystals, they have been discovered a long time ago to behave as smart materials. And on the left, we have the tourmaline, and it has been discovered in 1707 that if you apply a temperature difference on this crystal, it's a silicate, you will generate a temporary electrical signal. So you're able to convert heat into electricity. If we look on the right, it's the most classical quartz crystal that everybody knows, but it has been discovered so several years after that, but still a long time ago in 1880 by the Curie brothers, that if you apply a pressure on this crystal, you will generate electricity. And also that you have the reverse effect, the reverse piezoelectric effect. If you apply electricity on the crystal, you will have a slight deformation, small deformation that can be used. So this piezoelectric effect, piezo meaning pressure, to push, to press on the material, is an example of smart materials. And if we jump forward in 1963, another example of smart materials, here a metal called nitinol, it's an alloy combining the same ratio of nickel and titanium atoms. And this nitinol has been discovered to behave as smart material. And the story tells that during a meeting in a laboratory, the Naval Ordnance Laboratory, so which explain the null at the end of this alloy, nickel, titanium, Naval Ordnance Laboratory, as any meeting with material scientists, when they were presenting this new alloy, everybody started to twist it, bend it, manipulate it, and so on. And what is less classical, one of the people present in the room used his pipe lighter and started to hit the material with a flame. And what he observed is that the material directly turned back to its initial shape, so a straight wire, like if this material had in memory its initial shape. So the mechanism has been explained after that. It's also some crystal rearrangement, but basically the material is prepared in some conditions to have a permanent shape in memory. And even if you deform it and so on, when you're providing it some heat, some external energy, it will go back to its initial shape. So that's some example of smart materials. And this field has been expanded a lot at the end of the 90s with the progress in polymer chemistry to develop stimuli responsive polymers, materials that can react and adapt to change of their environment. And thanks to the toolbox of polymer chemistry, materials that can react to many different stimuli, chemical, physical, or biochemical stimuli, and provide many different types of responses. Changes in size, shape, to present sensing signal, change of colors, of porosity, of wettability, and so on. And it's very important to keep in mind here that the polymer chemistry has been really a powerful tool to develop this kind of materials, but also that it requires chemistry to be in close interaction with many different fields like physics, engineering, robotics, medicine, and biology. That was very important, and that's something that began really in the 90s and at the end of the 90s. So in this presentation, I will mostly focus on materials that are presenting some physical response, being change of their size or volume or shape, and materials presenting sensing behavior. And these kind of smart materials have excited the research significantly because people already had in mind that it maybe was possible to develop artificial muscles. So soft equivalent and synthetic equivalent of mammalian muscles. But if we go further, we can think about some other examples like the octopus in the middle. So actuating materials, but that are fully soft, not with a bone and skeleton of humans. And on the right is flying insect, for which small muscles are actuating wings. So smart polymers that could be able to develop, to enable all these type of properties. So just to summarize, a few examples of what is expected from these materials, not saying that it's already done, of course, but artificial muscles and soft robotics, bringing them in at the interface with biology, to develop them at micro dimension for microsystems, but also to integrate them in textiles to develop, for instance, textile muscles. On the next slide, I just presented some example of smart polymers. So if we look at them on the left here, this is a material that is that can be stimulated by a change of temperature. This is hydrogels, so polymer networks that will swell and expel the water reversibly above and below thermal transition. On the top here, hydrogels also, but that are sensitive to an electrical field. So if you apply between two far-away electrodes a high voltage, you will have an electrical field, and the material will bend reversibly in one direction or the other. On the top right here, liquid crystal elastomers. So rubbers that integrate on their polymer backbone, liquid crystals that will change their organization under UV light irradiation. And in this case, during irradiation, the liquid crystal elastomer will linearly contract. On the bottom here, shape memory polymers. So the equivalent, the organic and synthetic equivalent of shape memory alloys and materials that can be stimulated by a change of temperature and that will move and so generate mechanical work. And the last example here, dielectric elastomers, simply rubbers on which you will apply a high electrical voltage on top and on the bottom. And by doing so, what will happen? The material will compress and expand laterally. So you will convert a high voltage into a reversible deformation. And at the LPPI, what we are dealing with is ionic electroactive polymers. So we have the name Ionic, we have the name Electro, and I will try to explain how it works and how we prepare them. So this is soft materials that will contract and expand due to the diffusion of ions, smaller ions that will penetrate or be expelled from material under a low electrical voltage, typically 1 or 2 volts. So to develop this kind of materials, we need two components, electrically conducting materials and an ionic source. So the ions that are required because they are necessary for the working principle of these materials, and electrically conducting materials, which can be of various nature, carbon nanotubes, for instance, graphene, but also electronic conducting polymers. So electronic conducting polymers, I have to say a few words about it because it's a bit counterintuitive to think about conducting polymers. because for everybody, I think, polymers are materials known to be electrically insulating. And this is the case, for instance, if we take the most simple of them, the polyethylene, PE, which present along its polymer backbone a repeat unit composed of 2 carbon atoms separated by a single bond, each carbon atom bearing 2 hydrogen atoms. And this is a thermoplastic, which means plastic, it can be shaped, remolded, thermo, as function of the temperature. So this is the most common insulating polymers that you can even find around your electrical wires as insulating layers. And that's the case for most of the polymers. But there are some other type of polymers, which are called conjugated polymers, which behave a bit differently. And I'm taking here the most simple of them, the polytransacetylene, PA. And if you look at the structure, we have a double bond and single bond, one after the other, so alternating double bonds and single bonds. This specific configuration, this alternating structure, gives them this name of conjugated polymers. And in this state, the polymer is also insulating. But what has been very exciting was to discover that if you expose these materials to an oxidant, typically ion and vapor, you will, with the oxidant, oxidize it, remove electrons, and by removing electrons, what has been observed is that the electrical conductivity is increasing by several order of magnitude. So just to try to illustrate it, we're starting at a conductivity at 10 minus 7 Siemens per centimeter, so something that is typically insulating. And after oxidation, they can reach a conductivity as high as 10 to the 3 Siemens per centimeter. So it's, to give an order of magnitude, is not that far to some metals. And for this discovery, Iger, Shirakawa, and McDermott got the Nobel Prize in 2000. So their discovery is from the end of the 70s, 77 approximately. And they got the Nobel Prize for the discovery of conducting polymers, which has been called synthetic metals. And I really like the explanations they gave during their Nobel Prize speech. It was simply that if you take this kiddie game that probably all of you know, the goal of this game is to sort the numbers in the right order, okay? And to do so, it's quite obvious that you need at least one piece to be removed from the game to allow the other to move. And the principle of the conductivity, it was a bit simplistic, but at least it's a good way to remember it. By oxidating the polymer and by removing an electron or several electrons from the polymer chain, you will start allowing the others to move, and then you will transport electricity. So based on this, a lot of polymer structures have been developed because it was quite a small revolution to be able to develop electrically conducting organic materials. A lot of structures have been developed with different configuration, aromatic compounds, integrating heteroatoms or not. But you can see that on all of them, you have this alternating double and single bond all along the polymer chain. And these materials are very interesting to develop ionic electroactive polymers. Why? Because if you take your conducting polymer, in this example, polypyrrole, in the neutral state, and if you oxidize it, you're removing electrons, you will generate positive charges along the polymer backbone. Polymer positive charges mean that you will necessarily, for electroneutrality, have anions coming closer and will come in close interaction with the polymer chains. And what happens if you do that? So you immerse your conducting polymer in some electrolytes, a solvent plus ions. You apply positive voltage, you will remove electrons for the polymer chains, you will generate the positive charges, and the polymer will swell with a counter ion. You will have anions coming between the chains. This phenomenon is reversible. If you now apply a negative voltage, you will reinject the electrons in the conducting polymer. It will bring it back to the neutral state, and you will expel the counter ions, and the material will contract. And so you have a reversible and electrically controllable volume change that can be used to develop smart materials. So we have different configurations to get this kind of actuation. The first one, so you immerse the conducting polymer in some electrolytes, solvent plus ions, and when you apply the positive or negative voltage, the layer will simply swell or contract. If you now prepare some self-standing film, film that you can hand between your hands, long and thin, it will simply elongate and you will have this linear contraction. And now if you laminate this conducting polymer film with a passive layer, let's say paper, tape, anything that is passive, what will happen is that the volume chain of the conducting polymer will provide a bending deformation. And on this example, you can see an old video from EMX showing a linear contraction of this kind of actuator. It was a polypyrrole layer. And on this one, you will see a video coming from the laboratory of Toribio Otero in Spain. And the material will simply bend in one direction or the other because we have this bending configuration. The last configuration that I want to mention is that previously all these materials require an electrolyte, so they are immersed in a liquid electrolyte containing the ions. You can have this kind of behavior in open air as soon as you bring together two electrodes and you separate them with an ionic conducting membrane, which is in the middle and that will provide the ions necessary for this oxidation reduction process. And then you can get deformation in open air. So, okay, these materials are quite interesting because you can control their deformation with an electrical stimulation, which was one of the most convenient way to control smart materials. They can present large deformation, at least large bending deformation. They are activated under low voltage, which is good for power consumption, but also for safety. And safety, especially if we think about interaction with living systems, biology, cells, and so on. That's especially interesting since most of these materials have been reported quite many times to be relatively well biocompatible. But there are still a lot of challenges that have to be addressed on these materials. First, this is a nice small demonstrators, but also what about real integration, real application, and the mechanical robustness of these materials is definitely a question and a challenge. Second point, the lifetime of these materials, especially in the open air. If you take them out from the electrolyte, what will happen if you take out some piece of paper swollen like or soaked with water? Water will evaporate, and if the solvent is evaporating, the ions, the salt, will crystallize, and you will have no ionic conductivity, no ionic motion, and no smart behavior anymore. Also, what are the limits for these materials regarding their size? Can we make them large or can we make them small? And the last but really important question, what about their speed? Because if we are thinking about artificial muscles, we're thinking about basically mammalian muscles that are moving approximately at 1 Hertz. And that's definitely an issue with this kind of materials because they're relying on the motions of ions, diffusion of ions. And this is a phenomenon that is finally not so fast. So what is a strategy that has been developed along the years at the LPPI? We're a polymer chemistry lab, and we use macromolecular chemistry. And we work both on the electrodes of conducting polymers and on the ionic conducting membranes. Regarding the electrodes, first we have chosen a conducting polymer that at that time was not so common in the field of smart polymers actuators. It's a pilot, poly-3,4-ethylene dioxide thiophene. So why it has been chosen? Because it's one of the most stable conducting polymers. Unfortunately, if you synthesize this polymer in a classical way, you will get a powder that is not soluble, that you cannot fuse, and so on. So not really useful. And the strategy was to combine it with another polymer, which is not electrically conducting, but based on polyethylene oxide, PEO, because this polymer will bring first some mechanical properties to the material, and mechanical properties are important because we are dealing with electromechanical devices. There are classical polymers that are known to be good ionic conductors, and what we want is that ions being able to come easily in and out the film, and also because we have some chemical compatibility between the ethylene oxide repeat unit here and this ethylene oxide bridge that you have on the conducting polymer. And the strategy is what? Simply to synthesize the conducting polymer entangled, interpenetrated in a polymer network. And by this, we hope to combine electrical conductivity, mechanical properties, and so on. On the other side, for the ionic conducting membrane, the approach is a bit similar, but the idea is what? To develop polymer networks, or what is called interpenetrated polymer network, and I will talk about it just after. And these polymer networks are simply soaked and swollen in the electrolyte, and we have decided to work with ionic liquids, which are simply salts that are in the liquid state at room temperature, which means their melting point is very low. At room temperature, they are liquid, meaning that you need no solvent and meaning that you have no drying. So it's pure salt that will be incorporated in these materials and leading to what we hope to be air-stable ionic conducting membranes, which are called ionogels, so gels containing ionic liquids, ionogels. So the strategy is what? Simply to prepare first a polyethylene oxide network to develop this robust conducting ionogels. This PO network is obtained with two components. First, a monomer, and I represented here on the left. So for this monomer, a reactive function, a methacrylate, and on which it is attached polyethylene oxide chains in red here. And we will combine it with a crosslinker, a molecule very similar, but with two reactive functions at the two ends. And if you polymerize these two molecules together, so a large proportion of the monomer and a small proportion of the crosslinker, you will get something that looks like this, a polymer network with dangling chains, which are really known to be good ionic conductors when you put electrolyte in them. Unfortunately, these materials are very weak. If you manipulate them, they will break very easily. And the strategy was to develop this interpenetrating polymer network, the idea being to incorporate in these materials, to entangle in this first network, a second network based on an elastomer. The elastomer, for sure, is definitely not suitable for ionic conductivity, but will provide the missing mechanical properties to the material. And the goal is basically to arrive to this kind of structure, two materials interpenetrated into each other with a PO network and a rubber. So if we look at the properties of this kind of materials, we have two interesting properties for this kind of application: ionic conductivity and mechanical properties. And all the challenge here, that I will not detail, of course, but all the challenge was to deal precisely with the polymerization kinetics and the phase separation between the two materials to combine the two desired properties in one only material. If we look at the ionic conductivity, the values are not necessarily important. What is interesting to see is that the IPN, combining the PO and the elastomer, can present ionic conductivity relatively close to the one of the single PO network, meaning that the ionic conductivity will see its ionic conducting properties ruled by the PO phase, and much higher than what you get with the elastomer phase. On the opposite, if you look at the mechanical properties, the PO network presents, as I said, very poor mechanical properties, 4% of stretching and it breaks, while for the IPN, you will get almost the same mechanical properties than the rubber itself. And this is obtained because the two polymers are co-continuous through the whole material. And basically, when you stretch on it, you will stretch on the rubber, but ions will move through the continuous phase made of PO. And you can see on this video the kind of materials that can be obtained with good mechanical properties and good ionic conductivity. The next step is what? To develop these ionic conducting materials, these ionic electroactive polymers, to add the conducting polymer electrodes, the P dot electrodes. And the strategy has been this one, simply to incorporate in the membrane the monomers of the conducting polymer, the E dot. And after incorporation of E dot, simply by swelling, you will immerse this membrane in an oxidant solution. This oxidant solution is iron chloride, a well-known oxidant. And what we found out is that if you're tuning and controlling the solvent, the swelling ratio, the time, the temperature, and so on, it's possible to control the location of the polymerization. And what we saw is that usually the oxidant can swell very nicely the membrane, so the oxidant will penetrate the membrane, while the monomer will desorb very slowly. And if you're able to do that, you will promote the polymerization, not in the solution, not in the center of the film, but right below the surface. And the polymer chain will form here, and you will obtain this kind of structure with the membrane in the middle, but also the interpenetrated conducting polymer close to the surface, mimicking this tri-layer configuration that can be used for actuation in open air. On this picture, you can see the membrane after incorporation of the conducting polymer, so it's becoming fully black and shiny. And if we look at the cross-section, and we are doing a sulfur mapping, because sulfur here is a chemical signature of the presence of the conducting polymer, we can see these blue dots close to the surface and having this tri-layer architecture. So the next step is what to incorporate the ionic liquid, to stimulate it with a low voltage, typically 2 volts, and to get this actuation in open air. So we have materials that can operate in open air, that present large bending. The forces are also interesting to measure, and we have seen that the forces of these materials are in the range of tens of millinewtons, meaning that they can lift tens to hundreds of times their own weight. So that's quite interesting, but also that they're robust, and this was due to the design of robust materials using this interpenetrated polymer network architecture. So just a few examples of integration of these materials before moving to the rest of the presentation. Integration attempt. The first one was in collaboration during a CIFRE founding with a startup, BVS. The idea was to develop some biomimetic vision system. What they wanted to do is to be able to control the position of a camera by using 2 muscles, 2 ocular muscles, and the electrical control of these actuators and the signal of the camera were sent to an electronic board. The idea is what? That to mimic the vision system, and when you're looking at an object, what you do always is to put the center of what you're looking at in the center of your vision, because this is where you have the high resolution. The idea was that the camera is seeing an object, in this case, the blue color. The object is moving, and this information is sent to the electronic board that will, in return, control the position of the actuator to try to put back this moving blue color in the center of the image. So it was a very basic integration, but for us quite impressive because it was basically the first for us. And it has been possible after like many attempts because materials have been developed with robust mechanical properties. The second one with the same company was to mimic, to develop biomimetic rat whiskers. And you can see it's just a carbon fiber that it's attached to the actuator, and it's vibrating at a relatively good speed. And the idea was to mimic these rat whiskers for a small robot. What is important to see here is that it has been possible to combine in the material some actuation, some bending deformation under electrical stimulation, but also we observe some sensing properties that I will talk about later. But we have in the same material, like rat whiskers, actuation, and sensing at the same time. And last example on this type of materials is that since we are preparing them directly from monomers, from chemical reactants, we do not have necessarily to make them as films, but we can give them other shapes, and typically tubes instead of films. And by doing tubes instead of film, it has been possible in collaboration with John Madden at UBC to cover the left and the right of the tube with conducting polymers to mimic these tri-layer architectures, tri-layer configuration, and by applying a potential difference between the left and the right to get bending of the tube to mimic a catheter tip that would be electrically controllable. Well, so these materials are moving under electrical stimulation and are relatively robust, but we had a lot of work to do when we had to go to microsystems. And it's coming from contact, a collaboration that started with Eric Catan in IEMN in Lille, who came to see us and saying, oh, these materials are very interesting, very funny, but I would like to use them to make an insect fly. And definitely that was not something easy to consider. Why? Because these materials are not that fast, definitely not that small, they're relatively thick. We're cutting them with scissors, so we had a lot of things to develop to go towards this kind of application. The first step was to make them thin, And to make them thin was not necessarily the toughest part. Make them thin, it means to decrease their thickness, initially 250 micrometers, that's quite easy to handle, to decrease their thickness to few micrometers. So this can be done. You just have to replace the mold by a spin coating technique. So you deposit the viscous solution on a substrate, you turn fast, and depending on the speed of the rotation, you will have a thinner membrane and so on. So we have been able to obtain thin membranes, but also we have been able to control the polymerization and the incorporation of the conducting polymer to keep this tri-layer structure. And that was not so easy, but that can be done. And once you get these thin materials, the next step is to make them small. And to make them small, it requires not to use scissors anymore. The idea was what? To use a classical microsystem techniques, which is etching. You're usually using a plasma gas, you're exposing the materials to the plasma, and the exposed part of the material will be etched, and what you protected by a mask will give you the final shape of the material. And it's known that conducting polymers are not so easy to etch with plasma because they are relatively stable due to this conjugated structure. And what we found out was this conducting polymer is finally not pure conducting polymer or materials, but conducting polymer which is interpenetrated, entangled in another polymer, which is a PEO. And we saw, and we studied the mechanism here, that if you expose this material to a plasma, the degradation of the PEO will generate products that will attack the conducting polymer in a really intimate morphology and will promote the degradation of the material of the structure. And you can get by this way hundreds of microactuators at the same time without cutting it, but by etching it using photo patterning. So these materials can be made very small, but surprisingly, they can become also very fast. And that was very surprising for us, is that when you reach such thin materials and apply an electrical stimulation, you will see progressively the deformation decreasing when the frequency is decreasing. But at one point, what you will observe is a sharp peak corresponding to the resonance frequency, but which has been observed around 1 kilohertz. So that was truly for us amazing, because it means that at this frequency, we still have small ionic motion or vibrations that are enough to be amplified at the resonance frequency of the beam. And that's still today the fastest microactuators we reported able to operate in there. And these actuators have been then interfaced with artificial wings that have been developed by Eric Catton by using photoresist, and actuation of these micro wings has been possible. So does the insect fly now? No, not at all. Unfortunately, for several reasons. First, there's an issue, of course, of power source, because you need to bring the power source and you don't want to put a little backpack to the insect. But the main reason is that insect wing motion is quite complicated. That is not only flapping, it's flapping and twisting. And to reproduce this kinematic is basically out of the skills of polymer chemists. And this is thing that is still studied by the colleagues in IEML. But basically, we showed that the materials can be made small and can be made fast. But Eric Catton is not stopping here, and he asked us, okay, now I want to develop micro grippers. Can I develop micro grippers? And can I make these materials at home in his lab, in a physics lab? And this, it was really important for us to rethink completely the chemistry for him to be able to do these materials and not to do them in a chemistry lab. Why? Because in our case, we're using, of course, a lot of chemicals, but also a lot of manual handlings. And we were relying a lot on the skills of the PhD students that were able to manipulate these very thin films, to dip them in oxidant solution, to cut them carefully, to put them back on the substrate, and so on, even to put electrical connections. So, not going into details here, but what we have chosen is to use a commercial ink of conducting polymer, which is known to be relatively bad for this kind of application. But by using the same strategy to add this polyethylene oxide network in the presence of this ink, it has been possible to prepare these materials by limiting as much as possible the manual handling. And for that, the strategy was not to prepare the membrane first, to incorporate the conducting polymer electrodes and to connect them to a porous source, was to prepare them layer by layer, first electrode on the substrate, then the membrane, then the second electrode. And on this video, it's a video that has been done during a PhD project, which showing a bit how it's working. So first, the deposition of the conducting polymer electrode, so liquid one, that will be dried, basically at 50 degrees. The conducting polymer will become solid. Then the precursors of the membrane, which is this viscous solution that is casted on the top. Then the substrate will turn really fast, the membrane will spread and then will be polymerized to get this thin ionic conducting layer. And on top of this ionic conducting layer, you're putting the second conducting polymer electrode in the same way. Then on this example, it was laser patterning, cutting the materials into desired shape. And then these thin materials can be manipulated and placed between electrical connections. So at this step, manually, and then under electrical stimulation at 2 volts, we can get this kind of bending deformity. So next step was, after this preparation of materials, was to integrate them fully because, okay, microactuators, you don't want to put by hands microelectrical contacts. And I will not detail what has been done, but the colleague of IMN used a process, developed a process of photolithography and micropatterning to add, by using like layers, photoresist, masks, to prepare the materials step by step, which can appear to be quite a long process, but which, from their saying, is relatively classical for microsystems. But by doing so, it has been possible to obtain, without any manual handling, these microactuators integrated directly on a substrate and integrating directly the electrical connections. And of course, by doing so, you can develop materials with many different shapes. On this slide, you can see a membrane that will up and down to couple 2 beams together to have comb-like materials, like anything that you can have in mind for one type of application. And on this video, I'm just showing what has been done because the goal was to develop micro grippers. So the video is not very impressive, but I will try to explain it. Here, what you have is 2 fingers, 1 active finger on the left and 1 passive finger on the right. So passive, not that much. Passive, it's behave as a sensor. So 1 finger will be electrically stimulated, will bend, and the second one will simply record a potential variation and will behave as a sensor. And when you apply the voltage, the actuator will press on the object, and the object will be pressed against the sensing finger. Then you can see the sensing signal here in blue increasing, meaning that the pressure is here. And after a while, so the video will be accelerated, what you can simply do is apply the inverse voltage. By doing so, the active finger will actuate in the different direction. The finger will open and will release the object. And by releasing the object, you will see the sensing signal that is dropping. So that's a way to develop microactuators just using organic materials. And the goal, because here it was just the first demonstration, the goal is to develop micro grippers integrating muscle for the wrist and 3 fingers, 2 actuating fingers, 1 sensing finger, and even in collaboration with UVSQ to control them using a joystick with force feedback, meaning that you can even sense if you're grabbing an object or not, or if it's released. Okay, so I said a few words on the sensing. So they sense, and I would say, so explain a bit more about this. So they sense, meaning that they can at the same time actuate. You apply an electrical stimulation, you will have deformation, but if you press on the materials, you bend them mechanically, you will have a sensing signal. And from the biomimetic point of view, it's very interesting. This is called proprioception, and this is what you have in your biological muscles, meaning that if you close your eyes, you always know in which position you are because you have muscles that can sense at the same time. Or if you're grabbing an object, you know directly the weight of this object. And this is something that has been very intriguing for us and that we started studying approximately 10 years ago. And if you're applying so a force on the material, if you bend it, you will have a potential difference generated between the electrodes. What we found out is that it is not related at all with the conducting polymer, but simply to the ionic membrane, which means when you bend the material, you will have one side which will be compressed, so the pressure will increase here, and the other side which will be expanded, and the pressure will decrease. And by doing so, like you would press on a sponge, the liquid will travel and will move through the thickness of the material. And the principle is what you need is that one of the ions moving faster than the other. And it's possible if one of the ions is smaller, for instance, or one of the ions has more interaction with polymer chains. But if ions are not moving at the same speed, what will happen is that you will generate an electrical imbalance, even temporary, and generate an electrical signal that is proportional to the deformation. So we studied this particularly with the Professor John Madden at UBC. And finally, this investigation led to the fact that he simplified completely the system and said, we don't need the electrodes, let's remove them. And to simply have polymer gels, you put them on a substrate with even 2 electrical wires. And if you press on the gel, you will promote the ionic motion horizontally like this and measure potential difference. The idea here was that it was maybe possible to develop ionic skin with these materials. And I will just let a few words to John to explain how it works. So it was released at the TV news last October.
Press it.
It's in French.
Chaque fois que je presse, ça génère un courant électrique qu'on peut voir apparaître sur cet écran. Je presse, je presse, je presse. Une action aussi simple que presser cette gélatine génère un courant ionique qui est suffisant pour stimuler le système nerveux humain. Et tout ça sans électronique, sans amplification. Pas besoin de batterie, pas besoin de câble. Les premiers tests montrent que cette peau électrique pourrait ressentir aussi bien le toucher que la sensation du chaud ou du froid.
Okay, so basically, ionic gels, if you press on them, ions will move and you will generate an electrical signal, electrical energy. So we're far away from the completely over-the-top documentaries they made on television with bringing like sensing functions to prosthetics and robotics and so on. But that's the possibility, but really far away. Where are these work at the moment? You can see here on this picture a gel with an orange dot being the sensing part of the gels. And if you press on the materials, you will, as you see on this small graph here, generate voltage that can be sensed to quantify and localize the pressure. We have to keep in mind here that there is no power source because the generator is the gel itself. By pressing on it, the ionic motion will generate electrical signal or electrical energy. And what has been very interesting is that the voltage that is generated is in the range of few millivolts, and the current are compatible with interfacing them with a neural system. And what they have done there in Vancouver, so I put a little bandage here to not see how it is because it's lunchtime. But basically what we can see, so here, a hand is pressing on the gel, and the 2 wires connecting in the gel are connecting to the tibial nerve of the leg of the rat. And by pressing on the gel, there's a small electrical current that is generated that is enough. I hope we will see slight movement, so to interface the ionic skin or ionic power source with a biological system. So that's why the idea of bringing sensing functions to a prosthetics and to be able to sense, to give the feeling, the touch feeling to prosthetics rise, but there's still a lot of work to do. But going further in the interface of these materials with biology, I would like to say a few words about what we're developing in the frame of cell culture. Because these ionic electroactive materials can be very interesting for this purpose. Why? Because in vivo, the cells are surrounded because in a very complex microenvironment. It's a 3D and highly dynamic environment. First, cells are surrounded by other cells, of course, by proteins, extracellular matrix, soluble factors, but also surrounded by electrical, mechanical, thermal cues that will change over time and that will have consequences on their development. And it's very important to be able to mimic this kind of environment in vitro. So that's why over the years, there's a progressive shift on the cell culture from the classical 2D cell culture to 3D and to a 3D environment that is now dynamic and that we can call 4D environment, the fourth dimension being these time-changing properties. So it's very interesting because if you're able to do that, you can study much better the cell mechanotransduction, how cells behave in response to mechanical and electrical stimulation. If you're able to mimic better the in vivo environment, you can probably develop much more reliable drug screening assays, and maybe one day tissue engineering. So this is a work that we're doing in the laboratory with Cédric Plesse-Smart in collaboration with Johan Leroy-Dudal and Rémi Agnel. So the strategy was what? To develop now porous materials. No film at all, we want 3D. Porous materials. And I will simply start to explain how they are developed with this simple picture, the mayonnaise. Because if we look with a microscope at the mayonnaise morphology, it's composed of what? A continuous phase, aqueous phase, which is in black here, which is a phase with a very low amount, and the high amount is a dispersed phase made of oil, which means that's why mayonnaise is fat, and you don't have to eat too much of mayonnaise. But you have these particles that are almost touching each other. The idea was what? If you introduce monomers in the continuous phase, monomers will be just here in the black phase, and if you polymerize it, you will have a very highly porous vesicular materials. So of course, we didn't work with mayonnaise, of course, but the synthesis is very similar. You're starting with an organic phase containing the monomers, and you're adding a high amount of a dispersed phase. So in this case, the organic phase is a phase in which the monomer is. The aqueous phase will be the dispersed phase. At the end, you will prepare what is called a high internal phase emulsion. And if the monomers are polymerized here, so casting, photopolymerization, and after washing and drying, you will get what is called a polyhype, a polymerized high internal phase emulsion. So after washing, this is a kind of structure you get. So I don't know if you see well on the picture, but highly porous materials with pores in the range of tens to hundreds of micrometers. And interestingly, with a lot of little holes, little of interconnection between the pores. And if we look at the porosity and these interconnections, they have an interesting size for cells to come inside and to migrate through the material. So like this, the materials are completely passive. If you want to make them electroactive, you need to functionalize them with a conducting polymer to functionalize the surface of these walls of the porous material. And not going into detail, it's exactly the same principles that I was talking about before. You take these materials and you swell them with a monomer of the conducting polymer. The monomers will penetrate the walls. And if you fill the material and the porosity with oxidants, you will promote the polymerization of the conducting polymer within the walls of this porous material, which will turn black, but which will turn also electroactive. So you will cover the 3D surface with the conducting polymer. So question, does this electroactive materials expand and contract as we expect? So for that, we need an ionic source. So what is done is simply using the cell culture medium, which is full of ions, as an ionic source for this. The materials are immersed in this cell culture medium. We need 2 electrodes and an ionic source. So we're taking one electroactive foam, one electroactive material, scaffold. The second one, connected each of them by 2 electrodes, and you apply potential difference. And one will then be oxidized and will expand. The other one will contract. alternatively, and you have two actuating scaffolds. And this video is from last week, I think. We saw it in a meeting. So Francisca was doing our PhD on these materials. So obtained on the new confocal that we have here in the microscopy analysis platform. This is materials that can, I don't know if you, so materials that will expand and contract and move under electrical stimulation in the cell culture medium. So it's working. The biological electrolyte can work for this. Next step are they compatible with cell culture in general? So sterilization in autoclave have been verified. These materials are stable from their structure, so the 3D structure is preserved. Their electroactivity also. It has been investigated also regarding the cytotoxicity, and what we can see is that the polyhype functionalized with PDOT behave basically the same than the 2D cell culture reference. So no specific cytotoxicity. And if you seed cells on these materials, they will multiply over days, showing that we have cell proliferation. Are they still compatible with cell culture when you want to seed the cells in the material, and are they able to colonize the material? So cells are seeded on the top of the material, and the cross-section is observed like over time, and cells are quantified. What we can see that in the dotted line here in black, the number of cells is increasing over time. The number of cells is increasing and then behaves a bit weirdly for the top of the material, but it's increasing the number of cells. And the decrease here is what? Simply, the cells are not staying on top of the material. And if we're quantifying the cells at the bottom of the material, we can see that it's increasing. So, which means what? After a short time, the cells are still in the round shape and migrating into the material. But after 24 hours, they will start to settle and to attach in the pore like this, as a sign that they are not feeling too bad. So they're able to penetrate the material, to migrate, and to multiply. I will not detail this because I'm completely unable to explain it properly, but what has been observed is, are the cells feeling good? And they basically present the typical cell morphology of cells in a 3D environment. We can see here the tubulin, actin, and fibronectin that has been stained and observed under confocal microscope. And now the last stage, and this is where we are for these materials, it's the 4D stimulation. And this video, to tell you, so is coming from yesterday. So I'm really happy to show it to you, but it's the actuation of these materials, so electrical stimulation with cells, so red fluorescent human dermal fibroblast stimulated in the cell culture medium and observed in with this 4D video under the confocal microscope. So next step now are to study this mechanotransduction and to see if cell phenotypes can be oriented and to control this point. So we have now probably a nice 4D cell culture scaffold. And I will rapidly, to finish, say a few words, because I said that materials can contract, expand, can sense, but also can self-heal. And I will say a few words on the self-healing to finish this talk. So this is something really important, the self-healing of this material, because we're talking about electromechanically active materials. So we have to keep in mind that if you connect them to a device, sooner or later, due to their mechanical work, they might break. They're not, they don't have eternal life, of course. And when they're broken, it's basically just going to trash. The idea was, is it possible to provide them with self-healing functions like we would do, like we would observe for biological systems? So it's interesting. So from the biomimetic point of view, are we able for these artificial muscles to provide them with self-healing functions, but also from the sustainability, because we are hearing often that smart materials in general are the materials of the 20th century. But what about if these materials are also adding to the pollution and to the plastic and polymer waste? So is it possible to self-use them, to reuse them, or even to recycle them? So the challenge here, the question was how to heal cross-linked materials. And to explain this, I have to say a few words that are basically what you learn in the first lesson of polymer chemistry, I would say the first hour, you're learning that for the processing of materials, you have basically these three families of materials. On the left, the non-crosslinked polymers, which are usually thermoplastics, which are linear branch polymers. And due to the fact that they are not crosslinked, they are not attached to each other, if you increase the temperature high enough above what is called their TG, vitreous glass temperature, they will flow. So you can reshape them, mold them by applying temperature. You can also solubilize them. You're adding a solvent, the chains will solubilize, go apart from each other, and we have a solution. Meaning that you can recycle and reprocess them. On the opposite, the crosslinked polymers, and what we are dealing with here is crosslinked polymer. There's two typical families, elastomers and thermosets, and both of them, so they have different cross-linking densities, different mechanical properties, but for sure, it's impossible to solubilize them, and it's impossible to recycle them. And this is what you learn for the first hour of polymer chemistry. But there's been a little revolution like 10 years ago, approximately, by Leibler, who described cross-linked materials that can be self-healed and reprocessed. And not going too much into detail, but these materials are based on dynamic bonds that are able to exchange. So not to dissociate and reassociate, to exchange. And by applying temperature, this exchange allows the materials to be reorganized to change its topology. And on this scheme, it's like a really simplistic scheme, but that can help to understand what happens. You have a crosslink here, bonds created by two functions, and the third one will come. They will exchange, and you will have a function and a free group here. What does it mean? Is that you're never breaking a bond. You keep the cross-linking density constant, but the material can rearrange. So it has been shown for the first time on the well-known transesterification, and they have shown that once these materials are prepared, you put them in a solvent, they remain insoluble like thermosets. And if you heat above the temperature when this dynamic exchange is occurring, they remain insoluble. So they remain completely cross-linked all the time. But at the same time, if you cut these materials into small pieces, or if you split the material into pieces, it's possible to heal them, to reprocess them. So that was really a very exciting discovery, and there's a lot of interest into providing some sustainable properties and recycling properties to rubbers, like for car tires, for instance. There's a lot of work on it, and our question was, is it possible to do it with smart materials, and so conducting polymers and ionic gels? So I will not explain this chemistry slide, just a word. It's basically all the researchers open their old chemistry books to look for dynamic bonds and what can be used to develop this kind of materials. And in our case, what we have done is to try to pick the interesting dynamic exchange reactions that would be compatible with our materials made of ionic liquids, made of conducting polymers, and so on. And it has been possible by incorporating different types of functions. So it has been done on several types of materials in the PhD of Feng Dili and the PhD that of Croix in the frame of Utopia, so is defending in few months. It has been possible to provide these healing properties to ionogels. So when the material is cut, it's possible after exposing it to temperature to get back the materials in one piece, to bring back the ionic conductivity, the initial ionic conductivity properties of the material, but also most of the mechanical properties. And this strategy has been applied on the conducting polymer electrode also, and it has been made possible not to heal the conducting polymer, but to heal the network surrounding the conducting polymer. And if you had the dynamic functions in this red network, it is possible to get these self-healing properties. And you can see here a piece of the conducting polymer with two cables. We don't see, but there's a circuit going through here, this LED that is turned on. When the material is cut, the electrical pathway, of course, is broken. But after healing, we can get the materials in one piece. Electrical signal is passing through, the LED is turned on, and you can observe by this, by scanning electron microscopy, that the scar is almost invisible, meaning that you're able to heal the material. We are not recovering 100% of the electrical properties, let's say 50, 60%, and we are recovering most of the mechanical properties, but I would say in the same range of 75, 80%. So there's still work to do, but it can provide these materials with self-healing properties. So we're arriving at 1 hour of talk, and that's perfect because it's the end of my presentation. So as a conclusion, I would like to say that we are developing materials that are able to contract, expand, sense, but also, as I've shown you, self-heal. It's possible by the combination of electronic conductors containing conducting polymers and ionic conductors containing ionic liquids, thanks to the polymer chemistry and especially the development of these interpenetrated polymer structures. Of course, we're talking about artificial muscles, and as you saw, we're far away from artificial muscles. And if we think about artificial muscles, we're thinking about fibers, about contracting fibers. That's personally my researcher dream, to have one day these kind of muscles and maybe to combine them with sensing skin and so on. We don't have them, but there's a way maybe that is very exciting and that we're expect to develop. So I didn't have time to talk about it today, but it's the development of smart textiles to develop actuating textile muscles. Why? Because it's truly amazing field for me. Because it's a combination of microstructures, and we saw that if you're doing these materials thin, they can be fast. So basically, these materials are very well suited to be in the micro dimensions, but also the textile construction is a macroscopic construction that you can make large. So it's a combination of micro devices that can be made with a large surface. And this is something that is now understood in the laboratory especially in the frame of a European project, a doctoral network, which will gather 12 PhD students across Europe working on a smart electroactive textile, each of them on their own project. And one of the PhD students, so Gabriela Ananieva, just started in January, with the goal to develop actuating yarn and actuating fibers. The vision of the future is to develop actuating garments that you can wear in close contact with a body, to replace what is a state of the art today, this hard, rigid, and bulky exoskeleton, to provide maybe mechanical help for disabled people, but also to amplify and increase the strength of man. So I will finish, and I'm probably, and I apologize if so, but I'm probably forgetting people, but I would like to thank, of course, all the people who did the work and with who were working in the lab. So in the laboratory, first of all, Frédéric Vidal, of course, but Jao Nguyen and Cédric van Keysel also. Fabrice Goubard and Tantuan Bui, who worked on, who were working on the self-healing conducting polymer electrodes. Of course, all the PhD students that did really a great job, and hardworking PhD student and postdoc, Anna and Bin. The collaborators here at CY, Johan Leroy-Dudas and Rémi Aniel, who are working on the 4D scaffolds. Eric Attans, that you saw, was a really guiding colleague to orientate our chemistry to develop materials. John Madden at UBC and Arama Massian at NC State University. Of course, all the fundings for this, the work I presented today, and you for your kind attention. Thank you.